Uh,
Hello everyone. Welcome to another session of SD Skills. Today, Raghav is going to present a topic on algorithms used for the API rate limiter. So this would be a presentation and interactive session. So you can also chime in, put any questions in the chat, or you can ask real time. So with this, over to you, Raghav.
Thank you, Sim. Thank you, everyone, for joining this session. So, this session, we are going to cover different algorithms which can be used while implementing the rate limiter solution. So, this last week we had an interactive mock interview session where the question being asked to me design a rate limiter, and I particularly used token bucket algorithm in my proposed solution. So the ask was what other algorithms or what other solutions we can algos we can use in rate limiter. So we thought why not to present this as a topic to cover the rest of the algorithms. So I think most of you might be
Hey,
knowing what is
Raghav.
rate.
So, do you have the mock interview, that thing from the last time?
Mhm.
Yeah, so just to give more clarity to the audience.
You want me to cover up more what has been discussed in mock interview?
No, the design you created, what was that? On
Oh,
that
okay. Okay, so I
lucid
let me
chart.
yeah, let me check my lucid chat docs. Oh, luckily I have here. Yeah.
Yeah, so just give some like why the need came for this.
Yes. So if you see here, so I will take a step back. Thank you, Sim, for pointing out that. I will take a step back here. First, what is rate limiter? Rate limiter is used to control the traffic sent by a client or any service to your APIs or to your server. So in the HTTP world, a rate limiter limits the number of client requests allowed to be sent over a specific period of time. So here in this diagram, if you see, the client is sending requests and we have a rate limiter before it goes to the actual API servers. So we want to limit the number of requests. Basically, we want to throttle the number of requests is being coming to our API servers. So to do that, the main focus is how we can design this particular component or how we can throttle the request. So why it is required? There are multiple reasons. The resource DOS stuff like denial of service, resource starvation, or based on the plan. Every API provider has their own plans. Like per user can consume only 300 requests or 60 seconds. X number of requests, like that kind of scenarios. So here, when a question being asked to me, how you can design the rate limiter. So what I introduced an algorithm over here called as a token bucket algorithm, where I was proposing that I would be having a bucket where I would be putting number of tokens here. And if some client is calling my API, so we are always going to check this bucket, like, do we have any tokens available. So this tokens allocation would happen against each API endpoint. So say for example, if I have two endpoints, so and a client is allowed only to consume uh, five five requests per second or 10 requests per second. So what we can do is we can initialize our token bucket for that number of tokens based on the plan or based on the rules we have for that particular client. So once we have allocated those number of tokens in our bucket, then we would be having a counter component which would be keep on checking, okay, do I have enough tokens left? If we don't have enough tokens left, then I can let rate limiter know, okay, so this client has overconsumed uh, the number or the counter. So let's refuse or reject this request. Then we can send back to the client some kind of information in 4xs 429 or other response header information that you are overusing uh, the APIs or overusing the resources. So please try after a back of time. So this is a very high level thing. Um, uh, what is rate limiter and what we are going to do. And this is the little bit low level design presented in the mock interview, uh, where we presented that we would be having a different components called as rules resolver, resolve rules service. So what rules DB is, there will be multiple clients. Okay, based on the plan, every client would be having. One client would be having a premium plan, other client would be having a basic plan. Premium plan includes unlimited number of requests or more number of requests. So such kind of things would be storing against in the rules DB. So like this would, so again we have exposed a rules service. So rate limiter will check who is my client, go to the rules DB, um, fetch the information that client, then based on that decide whether I have to allow it or not allow it. If I have to allow it, then I have a request processor which can further route in our distributed system which server I have to send this request to. Uh, so yeah, this is pretty much. Then we were more talking about the distributed system. We would be having load balancer and how we can scale this rate limiter at every host level. So that is something which covered. And further question being asked to me, uh, uh, there would be a multiple host will be involved and counter information would be residing at a common place, how you can scale this further. And my proposed solution was we would be having some sort of common registry component, and every host can go and talk to that common registry to get and fetch the information about the counters, like shall I allow or not, because our in a pure distributed environment our endpoints would be deployed at multiple hosts. So that is something we thought. Then apart from that question being asked, apart from this particular algorithm bucket token, what other options we have? So in an interview, this was the only solution I had in mind. So during last week, I went back and looked into further what other options we have apart from this algorithm. So this topic or this session, sorry, this session is mainly going to cover this particular about how we can replace, what is the other options we have, better options we have, and what is the problem with these algorithms. Any questions so far? Oh, I will take a pause there. So feel free to jump in, guys, if you are not clear anything or if you have other thoughts here. Mhm.
This sounds good.
Okay, sounds good. If everything is good, then I will quickly jump to the algos part. Okay. So this is today's session. Uh, this the first.
I have a
Go ahead.
question. Like I joined a little late. Could you
Mhm.
explain, like just high level, what is token bucket, how it works, quickly maybe?
Yeah, I'm going to explain that right now in a couple of seconds. I'm going to start that. Yeah. So yeah, Sridhar has asked this question. So that is in fact our first part. So I will cover in this diagram how this token bucket works. So the token bucket works, if you see, these are the number of requests coming from your client or service. So it comes here and it checks the token, whether we have enough tokens available. And based on that, it forward the request to the API server. If it does not have enough tokens available, then we drop the request. So basically, token bucket. So for the better understanding in our simplified form, token bucket is just a container. Just assume it's just a container which has a predefined capacity. So tokens are put in the bucket at a preset rates, okay, periodically. Once the bucket is filled, so no more tokens can be added because it will do the overflow. Okay, so so I will. So the second diagram will makes more clear. So here, this particular container is nothing but it's a bucket or token container. So we are starting with 4 tokens. Okay, so 4 tokens means in a minute. Okay, I am saying that user can consume only four requests at a time. So what I will do, I will set my refill rate of my token bucket as 4 per minute. So so consider a scenario. We are at the first minute of the clock, okay, and our token is initialized with 4 tokens in a bucket, and we are starting with 4 tokens. So the first request comes, okay, this is the first request coming, and we look into the token bucket whether we have tokens. Yes, I have tokens. So I'm taking the first token and consuming it and marking it as or deleting it is consumed. So I have left with 3 tokens. Okay. Now at fifth second, I am getting 3 requests parallel. Okay. At the same time. So it means I have again 3 tokens left. So these 3 requests is gonna consume these 3 tokens and allow it to go further. So all 3 tokens. So after this stage number 2, I don't have any token left. And if you see, I'm at the 20th second. And in the beginning, I said my initialization period of refill is 4 tokens per minute. So it means refill is not going to happen in the middle of 1 minute, because still I have not completed the first minute of the time. So if at 20th second, if any more request is coming in, no more token is available, so simply we are going to reject this request. So with this approach, we are making sure that, okay, so what would happen when we are passing the first minute, we are in the next minute. So again, my token bucket is going to reinitialize or refill with further 4 tokens. So after this time, again, request would come, it will consume the token and proceed accordingly. So this is very high level how the token bucket works. Uh, does
I
it
have one
answer your
question
question,
here.
Sridhar? Go
Oh,
ahead.
yes, yes, it's very nice. Okay, I have one question. Say, so you said in your example of 4 tokens, right? Say user did some activity. For that, he actually need 5 times he has to call the API. Say some activity, say kind of signing. So that time he has to call five APIs. So, but the token contain the bucket contains only 4 tokens now. So how does that the complete transaction will not go through, right, for that user?
Yeah, so um so every token concept we usually apply at a single endpoint level. Okay, so if you have one endpoint which is having a nested 4 endpoints being called, so again, you have new buckets against every endpoint. And also it depends upon your business logic also, at at how much refill interval you are going to set for your bucket. It's purely depends upon your business logic. uh, but we are going to associate a token against each endpoint and against each client.
One more question. Let's say for first 80 seconds, none of the request came, right? And for the last 20 seconds, the 4 requests came, right? And
Yeah, so
started
there,
using.
yeah, that's a very valid question, Shashank. Yeah, so in fact, I also explored that part, and that is the reason we have some more better algorithms to cover that particular kind of scenario. So this particular algorithm has couple of problems. So to improve on such
Uh,
kind of scenario, we have some other solutions available, which I'm going to cover
uh,
in a short while.
Okay.
so what is the problem here? I did not understand this question.
So basically,
Uh,
like, I mean,
mhm.
this is for 1 minute, you have to use 4 tokens, right? But for the 80 till 80 seconds, none of the requests came, right? And all the tokens were there. But in the last 20 seconds, those many requests came. So it's an uneven distribution of what you say, load. I mean, in layman terms, like in the last minute, in the last 20th second, you had more peak, right? But for the rest 80 seconds, it was sitting ideal. So that's also in some sort of uneven distribution, right? Of parsing the request.
Okay, you're talking about the window concept, like.
Correct,
Yes,
correct.
yes.
Okay, so we should start from the window where you started actually. Got it.
But why would that be a problem? It's just like uneven distribution of the request. But
No, but see what happens in last 20 seconds, you got 4 requests. Now, when the next minute starts, again during their first peak, during first 20 seconds, you got request, and rest of the 80 seconds, it was sitting ideal. So for that, if you measure that 20, 24, 40 seconds, the server was for what do you say?
Okay. So,
I mean,
yeah, so
within a window, there could be some peaks where we can see the burst of traffic. So that's what I think.
That is burst of traffic you are seeing within that particular person. Something like that.
No, that burst is anyway we can't avoid, right? Even when the start of the window also, the burst
No, but
can
we
come.
can
But
fix.
we can only serve
You
only how many
can.
tokens are available, right?
So you can do some sort of like in 20 seconds consume 2 tokens, next 40 seconds you consume this. So by that way it will be even kind of thing, right? I mean, that won't be burst of
Yeah,
requests.
so
Something
the
like that.
last algorithm, yeah, I think these all are really good to see everyone is jumping in. Thank you so much for leading into this way. Yeah, we do have those kind of things also going to discuss in the last of this session. So I think which Shashank and Sridhar, everyone is talking about. So this is more like this kind of thing where you can handle that scenario. We
Exactly.
can do the sliding window with the counter hybrid approach, which is going to cover both things. Like we can make sure that um, the atomicity of a per 1 minute is precisely handled, and at the same time we are making sure that distribution of load is evenly spreaded. So looks like
And
what I can
also
do
you
is,
can make sure that none of the request gets dropped, right? In like scenario where you have 4 but 5 comes, so you can put that dropped request in a queue and pass it
yep,
back.
yep.
Oh yeah,
So
okay, it's there.
Praveen, yeah, that's a great idea. So you literally hit the
Uh,
head here, okay, which we're going to discuss now.
but the thing is, I mean, we can't save the request, right? Because client side will be having a timeout, and then we may re-trigger again, right? If we save that request.
Yeah, if by the time the timeout is happening, then business logic is going to remove that from the queue. Like it's
Yeah, then
already
you need to
timeout.
remove that from the queue.
That you remove it
Like,
from the queue. You can have a hard check kind of stuff there before processing
So,
it.
so you mean the timeout would be maintained similar timeout at the client side and the server side both?
yeah, you need to work with the business, right? All this is a high level, but the implementation will depend on your business client side, from UI side, and a queue side timeouts. So you need to work with that.
Okay, got it, got it.
Yeah. So I think, is it okay if I can move forward, guys? Yeah, so
Yes.
I think all of you have been already discovered all the problems about this algorithm, like even distribution, last minute short burst traffic, and to resolve these are all the challenging part, like how I can do the token refill, bucket size, and other stuff. And there are so many challenges are there involved to make it much better. So the next proposed solution is you can have a queue. Praveen already highlighted that part. To us, okay, so we can have a next algorithm called as leaky bucket. So leaking bucket is only one thing additional it has a queue associated with that. So by introducing a queue, we are making sure that okay, our request is being fulfilled at a particular fixed rate. Okay, so the token, it is similar to the token bucket, except the requests are at a fixed rate. Okay, but previously we are not having a clear idea whether it is going to be processed at a fixed rate or not. If your requirement of your project or your business requirement is this, so you can think of this solution. Whatever request is coming after the bucket, if bucket is not full, you can move it next and put it in the queue. And here you can throttle it to process at a fixed rate. So we are making sure that evenly distributed requests are coming at a particular fixed rate. So then the request can go through. That talks about the leaky bucket algorithm. Um,
Yeah, can I
I,
ask you here, how
Mhm.
can we use leaky bucket for HTTP?
Just we have to have one component at a proxy level before it hitting to the actual API server. So maybe your load balancer, once the request is coming to your backend, so before it hit to the actual API endpoint, it should hit to your component first, which is going to rate limit the request. So every request is going to pass through that component. So
Yeah, but
that's
if we use
Mhm.
HTTP, we cannot queue a HTTP request, can we?
Um, can you little, so I'm not clear about your
Yeah,
question.
I'm
So
trying to understand if
the way
how
HTTP works, you are
yeah
sending the request, okay? So now
yeah
the request is sent to the server. Now server is going to respond back to request,
yeah
okay? So
as I understand, I cannot put HTTP request into a queue. Yeah.
So by
Which,
default, it is, but you can enable that feature, right? Can be enabled as per based on the pool basis. Like you can designate like 120 requests would be the queue length.
is it question at like a Tomcat server level? How many pools, how many parallel connection we are going to open? Is it something like that?
Mhm. But so it look like every user will have its own queue. It does not like, right? Because one queue for each user. So we have two users, we're gonna have two queue.
That depends, right? We can maintain the queue per user, we can maintain per IP address, or that depends on how our, like, on what basis like we're fixing these buckets.
Yeah,
so
but
there are
normally we based on the user, right? Let's say on the user token. So each user going in, we have to have the bucket, or in this case, we have its own queue.
Yeah, as already highlighted by I forget the person name. So it all depends upon the business logic. So when you are initializing the first request, that time we can build up a queue, initialize the queue against either at IP address or at a client level.
That means we would have log queue on per server.
So generally, you have to keep a queue or some kind of similar to queue, because you can't, for auditing purposes and for tracking purposes, like what got dropped or what events needs to be reprocessed or the request, you need to add that to the queue. If the queue is within the timeout range of the request response, then then you will get the queue responded to the front end. If the queue is outside the timeout range, then you will not get any response and you will get an error, and you will track that, like you will drop that from the queue.
Yeah, I think that's related to Nikolai question, right? Maybe that was like, I think maybe he mean like each, HTTP request will have its own queue to queue the connection.
I don't get it. HTTP. So what happens is when you give the HTTP request, supposing you're doing a payment, right? And you want to do a payment. So the payment page will be sent to the backend, and you want to rate limit how many transactions go through. So the payment page will be like grayed out or something, and then the transaction will go back. If the transaction doesn't come within the certain time, you'll give a default response, like circuit breaker kind of thing. Like if the response doesn't come within certain time because of rate limiter or some backend issue, you'll see timeout or some retry. If it comes in a specified time, then you will actually give that success response from the backend.
Okay.
So I have one general question here. For the payment system, does any system do this limiting the rate? Because payment anyway, they want it anytime. If somebody pays, why we need to stop him?
What if somebody is unnecessarily hacking the system, hammering away?
Yeah, every
Usually,
has for
most
denial
of
of
the
service, right? Because you get charged every time you use the payment gateway. You have to you get charged by third party, MasterCard, FIS, and hundreds of other systems. So they won't let uh, someone to get burst unless you are expecting a burst of traffic, like you are opening a reservation to a concert or a ticket to some airlines. Then they preemptively give those rate limiting. They increase that from 1,000 to 1 million, but they don't give that forever. They generally always throttle it because every transaction costs, even if
not
it's
in,
success or failure.
There is one point I want to add, right? You can have a rules on the API layer level, like API gateway or anything, assuming that the same request is coming from specific IP address. You can apply the throttling logic, right? You can able to do like that. Depends, right? Depends on the company. You can able to do all this logic. The only problem I noticed this queue is, right, if you have a 2-3 servers, how the queue is going to handle. I'm not sure actually this architecture, because if you have a 2-3 servers in the load balancer, right? If you have a queue, how the queue is going to distribute on the multiple servers. So your question is, this algorithm has some disadvantages compared to which other
No,
algorithm?
I mean to say the queue.
No, I know, but this
I'm
algorithm,
assuming
this algorithm has disadvantage compared to which other algorithm compared?
I mean
So
to
far as
say
queue
the
is concerned.
how it is going to handle the distributed queue, right? If you have a 3 servers or 4 servers are there in the load balancer, how you are going to distribute, how you are going to know that, okay, if this message came to this
got
server,
your question.
right? How
I
are
got your
you going to
question,
do?
but my question was, so are you aware of any other algorithm for rate limiting which does not use a queue and is better suited?
Yeah, I don't think so. People use the queue actually. If you know Google APJ gateway, if you use the queue, right, what happens is it has
No,
to
my
be
question was not
distributed,
about the
right?
queue. My question is, are you aware of any other alternatives which doesn't use a queue?
But I don't think so, right? If you use the queue, how it is going to, if one server goes down, right, how it is going to handle, right? How request is coming through? How do you know that it has to come
I
back,
know,
right?
I understand your question, but do we have an alternative here?
There might be, yes.
Sliding window
Definitely
is there,
the
right?
file-based system or something like that, you can maintain it. According to that, you can able to do, because the queue is more onto like a, if you are doing at the business layer level, it makes sense, asynchronous process, right? In the web layer, how are you going to maintain the queue in the distributed environment? Tell me that, you answer me that question.
Yeah, what was the
Tell
other
me that
alternative?
is the
you
major
said?
drawback here. I'm not worried about the algorithm or anything. If you have a 4 servers, if you use the queue, how are you going to handle it, right? That is a major problem. That is
So
a
what was
question
that
you ask
other
when
alternative
you
you
go
said?
for
The
interview,
file
right?
based?
Huh?
What was the other alternative you said? File based?
Yeah, file sharing.
So
Actually, you can able to do.
Why can't
that.
this queue be distributed if you use a in-memory, if you use a in-memory distributed cache like Redis or something? So where we can have a distributed queue, and lot of and there are algorithms which does use Redis for that this rate limiting. So that this queue can be maybe like a time based.
How do you know, right? Queue is like a first come first serve, right? How
queue
do
can
you
be
know
distributed,
that?
right? Queue can be distributed.
Correct. Queue is distributed, right? I agree with you. How do you know that, okay, this message belongs to this web server, right? That is the problem, because it has to be dynamic. That is the drawback, right? The queues and all the stuff is the talking is very good. When you go into the distributed asynchronous process, it works very well. But when you do the load balancing and then if you have multiple servers, it won't work. If you go look like APK gateway, which is developed by a Google, it will, you guys can get it the idea actually. Because I'm just giving, right? I'm not negative about what you guys are doing, but that is my feedback,
So don't we? That's very good, valid thoughts, Vijay.
Yeah,
Thank
I'm
you
not
for
telling
chiming in.
like
So don't
yeah.
can we think of that our load balancer come into picture after the queue, and this itself is a distributed one? So
no, not like
can't we
that.
think?
See, I will give. I have a idea about APG gateway, right? Google has a APG gateway. You can able to have multiple rules, right? How do you want, right? If you want to like restrict based on the IP address, or within the like a duration of 60 minutes, I'm only allowing 60 requests for a minute, right? Based on those rules, then your throttling is come into the picture, right? Now in that situation also, if you have a 3 servers, how do you know that you reach 100 number, right? Those things you need to have some global memory or a distributed memory which can able to handle it accordingly. But sometimes it can cross the number too, but that's another drawback, right? Those are the rules based. Once rules cross it, right, remaining will be, everything will streamline. If you understand what I'm trying to say, throttling will happen
After like you are updating the flag, right? You are reaching certain number, right? Then you are updating. Now you need to think about like, okay, it reaches 60 number, right? It is just like a sliding window. Everybody is algorithm, right? Sliding window has to work on the global scope. Once it reaches this number within the time frame, time bounded sliding window, that's where they designed the architecture, not the queue. Queue is a first come first serve, right? Now you don't have a control, expiry and all those stuff you need to maintain. Those things, it is similar thing, but it is not into the queue based architecture. You just need to count that how many requests are reaching, right? You need to have a rules. Once it reach your servers, you have a 3 servers. Once it reach server, you need to
So Vijay, I mean, you are saying like we need to maintain a global state, right? So that we can maintain a global state for every user. So whichever server picks the request, they update the state in the global state. So in that they will maintain what is the how much number of APIs we served for him. So that way we can maintain, right?
But there can be race condition also, right? In that case.
Yeah, exactly.
So
no, race condition,
if
we
both
have a
requests
model.
are reach same place,
no,
right?
How do you hold on a second. Hold on a second. To solve the race, we have many models like single master, multi-master, masterless. So by using those architecture, we can solve the problem to some extent.
So can't we replace this queue with the Kafka itself, right? Every partition will be dedicated.
I mean, the queue means he's talking about Kafka. Kafka also
queue, right? These all like whatever you guys are adding these things, right? Queue or a distributed queue, right? It is very, very well. Think like queue or like a memory based queue, right? Both are same, right? If you distributed queue, you can use any Redis cache, or memcache doesn't work. Memcache is local. Like if you look Redis cache, right? It will work, but it is not meant for like a quick response, right? You need to give fraction of milliseconds or microsecond, you can say. When the request is coming into the web server, your request has to be quick, right? When you use the queue and all the stuff, those are asynchronous process. Means you are going to see big delay. If you want to get a quicker response, it has to be in memory or some file base or some kind of a mechanism. It has to be so that you need to handle the race conditions and all those. Those are the way you can handle it. But very high level picture, you can think like a sliding window with the time bound, right? Depends on the rules, what it is. You need to control on that, right? You're reaching into 60 minutes window. How many requests has reached that one? That's where you can design it. It has to be quick. Yeah, that's my approach.
Yeah. There are different rate limiting algorithms. So till now he covered the 2 of them. I think the sliding window is next. There are a few more. So there are various that I think that's what the intention of today's session. We are going to cover the different rate limiting algorithms, and I think we are on the second one. Sliding window, again the log based and all. There are different approaches. I think like he's going to cover
so
next.
Just to add one thing, if we replace that queue with the direct service, wouldn't that solve the problem of delay?
But if you have a 3-4 server machines, right, in the load balancer, how do you handle it, right? That's the tricky part. Because it is not like this, right? You can put every request as a threading mechanism. Then what happens is you update into the database, record is updated, and then based on that it happens, but it is a slow process. It will go to the database and do, right? There is so many mechanisms are there. Those are like a very slow process. Even if you use a queue, right, it's slow process. It doesn't help you with anything.
So what you're saying is that in general, it's not a good idea to have a queue for rate limiting kind of algorithms if we have an option, is it?
No, it is not like a rate limit. The queue is not option. The thing is the queue is a good candidate when you want to do asynchronous process, right? You don't worry about that when your response is coming through, right? That is the use case you can use it. I'm not telling you I don't want to use it, not like that. The use case is different, right? You can use the queue, in-memory queue, you can maintain certain things, but it is slow, right? You don't get a quick response. You don't have a control.
Okay.
Because first come, first serve, right? But in this case, you're not looking at that one, right? You're only looking like, does I reach the limit, right? That's the only thing. If you reach the limit, basically you need to maintain that until it reach. It is more like a, I mean, my opinion is more like a sliding window kind of stuff, and then it doesn't have to maintain anything. It is just like a counter. You are maintaining the counter, distributed counter, you can say. very high level
Yeah.
picture.
I think, yeah, valid thoughts, 100%
Mhm.
agree. I think the queue mainly solves only one problem. That problem is processing at a fixed rate. If the business requirement has that requirement, okay, I want every request to be processed at a fixed rate, then only we can think of a queue. Correct me if I'm wrong.
See, queue is good for you, like think in this way, right? Rate limit, right? The thing is, there is a two-step process, right? First step will be when the request is reaching into the server, right? The entry point itself, you're throttling, right? That is the stage. It has to be very quick, right? Assuming that, okay, you are not reached the limit. The next step you want to put in the queue, and then, let's get the response back and all the stuff. It can be the background process, right? That's our like asynchronous process. You want to do it. But the first step using the queue, I don't know. I don't see it is ideal solution because the queue is slow.
Okay, let's compare when we're using a queue with using the bucket token, previously. What what are different? The difference is, in the bucket, we allow to process multiple requests at the same time, right? But with the queue, we only allow one to process one request at a time. That's a two different. So, if we use a bucket token, previously, and let's say, after the bucket token, we have another queue, after the bucket token, then they're going to be the same as using, the queue on the second.
Yeah, but usually when we're talking about bucket tokens, they does not use any queue. They use just counter and filling rate.
Right,
yeah.
right. But that means that allow, let's say you think about the request. If they granted the request, that means the request can be processed right away. That means you can serve multiple requests at the same time. With the queue, we only serve one request at the same time.
So more latency will be there in this case, right? Because rest of the request will starve till the first request gets served, right? Which is not in the case of a first algorithm. I mean,
yeah, but that's still related to how the number of parallel requests you served. You allow to serve, right? But the only difference with the queue is I see only one request for per queue, right? Only one request being served at a time.
So when you say multiple requests can be processed by the first approach, are you talking about fanning this, let's say 5 requests to 5 different servers, or is it still being serially executed by one server?
It's just like you don't have a way to throttle it. You don't have the way to limit, you don't have the way to control like how many requests can be served at the same time. And that is a problem when the bus, right? You have a lot of requests coming in and your server is going to be really busy. Versus you throttle it.
Think in that way, these two algorithms. In the first one, you have the bucket, and then you are putting the token in the bucket, and when request comes, you pick the token from the bucket. In this leaky bucket, you can think like that. Instead of putting the token in that bucket, you are putting the request in the bucket, and you are pulling the token from that bucket.
So in first case, can multiple, 5 requests at the same time can pick one token and get processed parallelly, which is not possible in leaky bucket.
Yeah.
So here you just fill all the requests in the bucket, and your business logic pull the request from that bucket in a fixed rate.
But again, in this case, we have disadvantage, right? Like other process will have to wait before the first gets processed, right? In leaky bucket, because queue we are putting.
But still, you have the same. You will process the same amount of requests.
Yeah, but there simultaneously all those requests could have been served, right, in the first approach, which is not possible to serve simultaneously.
Yeah, so that's why whatever was the issue with the first algorithm, this Leaky bucket solved that. So you are having a burst in that around the edge or somewhere in the middle. But now here with the Leaky bucket, you smooth that process. You execute the request on the same at a fixed rate.
But I think it added more problems, it looks like. No.
Like what?
like, I mean, see, in previous case, like if 5 requests come, they can pick the token and parallelly they can be processed, right? Which is not possible here. Simultaneously, all the 5 requests can't be processed, right? It has to be in queue. First will go, and then, I mean, FCFS order, right?
The
Yeah,
queue is
but
based on
within
the
that, so let's say your limit is that you have to execute 10 requests in a minute. So in the first one, you are executing 10 requests in a minute, but could be possible that those 10 requests were in the first 5 seconds, last 5 seconds, or middle 5 seconds, right? But here
Yes.
again, you are allowing only 10 requests within that minute, and those 10 requests are uh, distributed throughout that minute.
Yeah,
Okay.
equally fixed rate. Yeah, you are right, Praveen.
other than starvation, right? This is much more stable in terms of picking the request.
Yeah, it
Yes.
fixes the one problem from the last algorithm, the rate of processing. The here it's a queue, and from there it could be a fixed rate. But this algorithm can also suffer from the burst of traffic. Let's say
Denial of service attack can still happen, because if someone does 1 million or 2 million invalid burst of traffic, then the traffic that comes after 1 or 2 million, the genuine traffic will actually be sitting in the back of the queue and will be suffered.
Yeah, so what I mean to say is, like, we had like 2 problems in the previous algo. So this fixes one of them, but there's still like there is a 1 minute window, and let's say our queue is empty by that time, and our window started, let's say, like the start of 5 minutes 1 seconds, and 5 minutes 50 seconds, and let's say the queue size is of 10, or the bucket size. So still within 10 seconds, those requests will be added to queue. So the burst of traffic, that problem will still be there. There are other algorithms where it can be resolved. So that's what I could understand from these 2 algorithms.
Yeah, I think everyone has valid thoughts. Really glad that everyone is pitching in, Rajesh, Praveen, Shashank, everyone. So I think every algorithm has some pros and cons. And if your requirement is processing at a fixed rate, then go with the queue approach. And the cons is like burst of traffic is going to fill up with the old request if they are not processed on time. And as Praveen, the person said, the new genuine request would be taking more time than expected time. So with this, is it okay if I can move forward to the next algorithm?
Yeah,
Because
just
we
the last
have a
question.
time.
Yeah. Just the last question.
So that's a
Do
good
we-
discussion, and we can maybe we can go back anytime and specifically give a elaborated session only on one single algorithm. So I will go to the, with this note, I will go to the next algo, which is called a fixed window. Again, this is not sliding window. This is again fixed window. We are going to cover sliding window in the end after this. So I will quickly explain what fixed window says that. So fixed window says that we are going to divides the timeline into the fixed size time windows, and we are going to assign a counter to the each window. So in this example, if you see here, so we are distributing the timelines after every one minute, okay, like, and with the size of counter max 3. Okay, if some in one particular minute time window, if more than 3 requests are coming, then they are going to limit that request. These 3 will not go to the processing. So this is very high level. So whenever each request is going to fulfill, behind the scenes, we are going to increment the counter by 1. And once the counter reaches, in this example, clearly counter reaches to the 3, we are going to threshold or drop until the new window starts. Okay. There is a major problem with this, okay, this window concept. The problem here is, if you clearly see, the requirement says that 10 requests per minute, or 5 requests per minute. Okay, but if there is a overlapping of a minute, then the problem comes. What is the problem here? The first 5 requests in the middle of this minute, okay, for the better we took a minute approach. So this is the window for 1 minute, this is a window for the second minute. So the 5 requests came in the last 30 seconds, okay, and another 5 requests came in the beginning of
the next minute. Okay, so in total the 10 requests is passing, because still it is a valid window. Okay, so that is a problem here. So it is allowing to pass more number of requests than expected. So any thoughts here, or I can directly move to the sliding window, which is everyone interested in.
Could you please highlight a difference between this one algorithm and token bucket, because token bucket looks the same, no?
And can you increase the font also? Like it's a bit small.
Oh, actually, I took the snapshot of the image from Alex's book.
Yeah,
Maybe I can zoom it.
You can zoom it actually, Shashank. You can zoom from the screen.
Okay.
Is it better now?
Yeah, it's fine.
Yeah, feel free to jump in, guys, if you have any other thoughts here.
Is the assumption in all this solution that you have a distributed writer, DB, some sitting somewhere?
Sorry.
You need a distributed storage, right? In all this, in this particular solution, which has to accept this per user or per session. You need to have these counts stored.
Yeah.
Is that the default assumption that we have a distributed storage, like Redis or something like that?
Sorry, I'm not still clear on that part. Like you're saying that
where are we storing
information
this?
We are going to yeah.
Where are we storing these counters?
Yeah, we can share it to store it to the Redis or any other distributed system which we have. We made that assumption.
Hey, what is the difference between this algorithm and the previous algorithm? As Nick has asked, actually, could you explain that?
So, I mean, as per my understanding, like the previous one was the limited by the bucket size. Here,
it's a time
which is limiting the I mean the window.
But other than that, nothing looks different, right? Just they are maintaining a time. That's it, right? There also within 1 minute, 5 tokens has to be used. Here also they are just sliding a window concept they have introduced.
So I think like there it was not a time. I think I also said it, but it was wrong. So I mean that's what my understanding is. With token bucket, the bucket, I mean it could be filled in 1 minute or like.
But here, if you see, there in the previous one we have a container. Okay, so container would be having, let's suppose 5. If that is done. Okay, but here we don't have that one, because here, if you this example, we do not have one single bucket which would be holding this one. We are going. This is pure dynamic.
Yeah. I think in previous approach, it depends on how one request. It depends on rate of request, how a request is served. In this approach, I think it is fixed that in a given sliding minute, we can only serve 10 requests. But in previous, it depends on like a rate, the rate, maybe outflow rate, something we can call.
No, I think the previous one, right? So even if you have request or not, we are fixedly timing wise, we are giving the slots. So this is slot, this is the number of tokens available.
Yeah.
If your request comes at the last minute also, your opportunity is over. Whereas here, whenever the user request comes, from that time onwards, the window starts. So from that point onwards, you will be solved these many number of tokens, you will get it.
No,
and then there is a timeline. So like
but again, in that window, if it crosses the limit, right, it will throttle it again, right? Like in this for last 50 seconds and first 50 seconds. Here 10 requests came. Capacity was only 3 only, right? Or 5.
Yeah, so that's the one of the problem as he explained with this approach, because with the fixed window on the edge, it may serve the double request.
So one difference I find between this and bucket is that if you were to tell me to code this, I find coding this will be much simpler than bucket one. I think with the bucket, I might to introduce another thread which will refill the bucket. But with this one fixed window, it's very simple. I just take the current timestamp, I eliminate, let's say it's per second counter. I just truncate the second portion and just take the minute. It's easy to code.
Yeah, we don't have to use extra memory in this case.
Memory, right? Counter you will be using, right? Bucket, typical bucket, you won't. I mean, a counter variable only would be used in the leaky.
Still, queues and other things are going to consume a lot of memory, but compared to that, it is much memory efficient.
That for implementation, right?
Those are implementation specific, right?
Yeah.
So we should not mix the design and implementation. Somebody can come up with an efficient algorithm to maintain just one bucket for everybody, and he will make sure these many tokens will be served to the each user. So that all implementation. I think we should not mix that and design it.
Yeah,
there are ways to implement even better than that.
I know that it's implementation detail, but I had the same question again earlier. Also, I was asking: are we assuming that we have a storage somewhere we are storing all these counts? For example, if I am rate limiting by IP address, probably. So, if for that IP, I need to make sure that I have a window, and in that window, I am well within that limit that I have. So that means I need to have a kind of distributed storage, because that request can land up in any server. If I have a distributed, so is it the default assumption that I have a distributed store, or somebody talking about queue and all? So how will queue work? Because that would be like pertaining to one single node, right? So I joined late, so maybe I'm missing some context.
Yeah, and I also shared two link to code of Envoy, yes, for implementation token bucking. And token bucking in Envoy does not use any queue. It uses just two variables, number of token in the bucking and refill rate. Yeah, so we don't need any background process to refill a bucket or something like this, because each time we know how many and what is the time of the last access. Yeah, we can understand how many token could be in the bucket each time we call a function.
But bucket token, won't that need another thread to refill the bucket?
No, it does not need. You can look at source code of Envoy. I have just sent a link to our chat, yeah. And because we know last time of the last request, yeah, and we will always understand how many buckets currently in the token, or how many tokens currently in the bucket.
But what if the last request never came? Then we will never refill the bucket, right? If we are doing it in a single thread.
Yeah, but next request will refill. It's logical refill. It's not a physical refill. We just need to know a number of tokens in the bucket.
So I think that's a hint of the difference between bucket and fixed window. In fixed window, if we don't use the previous request, that's gone. But with bucket token, I think maybe it accumulates over time. So if no request has come for 5 minutes and the limit was 10 requests per minute, then the total request still left now is 50 in the next minute for what is that first approach, the token, bucket token. But with fixed window, it's always going to be 10 requests. If you didn't use the previous one, you lost it.
That's not true. I mean, in the token bucket, if bucket is full, so your token will overflow.
Oh, is it? We don't just keep adding, is it?
Yeah.
Okay, then back to square one. Sorry.
Oh,
I thought I was a smart one here.
so can someone summarize the difference again between this, fixed window and the token bucket? What the difference?
No, the difference here is you have daytime traffic and nighttime traffic, right? So you set that throttle so that you don't. So during the daytime traffic, you can enable more pods and machines, and nighttime traffic, you won't keep that. So in that sense, fixed window is kind of better than, whereas token bucket is forever constant like that. Though you can do this, almost use the same implementation of fixed window in token bucket, but out there in token bucket, it's like how much tokens you are given within a certain time. Whereas out here, you are just maintaining the window. In that window, how much you can give.
Or with the token bucket at night time, you can set the token size, to be different.
I know it's the certainly if you make some changes, you can actually implement the same thing. It's like implementing stack in queue and queue in stack.
I think in token bucket, right, say there's an overlapping, right? Say there are two buckets are there, there's overlap, and your request came at the last minute of the first bucket. So then until, so say you have only two, you got one kind of bursty traffic, but the time interval is over. So you need to queue, right? Other request. So, and then if you get a new tokens, those requests will get served. But here in the second approach, so the interval starts where the request will come, right? So from there onwards, they serve the continuously without even doing any queue until those many number of tokens are available.
This is not a rolling window, right? This is the fixed window.
This fixed window, yes.
Yeah.
So I'll try once again.
Yeah, the window is fixed. The window is fixed, but the thing is, they will start only when the burst comes. I mean, wherever the first request comes from there onwards, the window will get started.
That's no. Okay. So you mean talking about the you mean the token bucket?
So let me try another. Again, I'm trying to pitch my old argument that in token bucket we can have this option in token bucket of accumulating all the old unused token. So let's say the use case is, let's say I use my cell phone and I have some free minutes, and the free minutes can accumulate over time. I don't lose it in some plans. So with token bucket, you have that option. We can add that feature of accumulating unused token, but with fixed window, there is no option available.
That will become rate limiter. It's not rate limiter anymore, right? The rate limiter, you have to reset it to rate limiter.
Yeah.
So my understanding is basically a token bucket is an implementation, and you can use the token bucket to implement fixed window or sliding window. If your bucket width and your fill rate same, then it becomes fixed window. If they're different, it becomes sliding window. So that's my understanding based on what I studied so far. It's basically implementation. Depending on the parameters you choose, it can be fixed window or it can be sliding window.
Okay, and if we look this the entire thing like tokens as like, if I register for a service, I get 60,000 tokens, and if someone else registers, he also gets 60,000 tokens. And now basically the problem is both of those come to same server, and we can use our tokens, and those will be guided to the sessions, to the servers. And when that happens, these sliding windows help from the server's perspective, that either you have a fixed window or you have a sliding window. So that way we don't just burst the server, and the tokens are from users' perspective.
So my understanding how it goes is like, correct me if I'm wrong, guys. I think great thoughts are pumping in here. For this fixed window, the actual initialization of the bucket or backend, whatever you're using data structure, it's going to start the minute you are getting the first request in whatever time frame you are getting. Is this a right statement?
No, fixed window is always going to be the fixed minute request, right?
Sorry,
that's the other algorithm. The fixed window, that's why it's called that fixed window. It's the interval is always fixed, like it could be a minute or 5 minutes or 20 minutes or 24 hours. Those intervals are fixed.
The intervals are fixed. So say for example, but the calculation of serving the request is wrong here in the fixed window.
Yeah, so that gets resolved in the next algorithm, which
problem. So the problem of this algorithm is my calculation is always a minute, no matter from where the start and end of the minute.
No, the problem with this algorithm is it's the window is always fixed. So here what happens, like 2 to 2.1 there is a window, 2.1 to 2.2 there is a window. Let's say our request size is 5, but what we see is from 2.5 to 2.15 or like 30 seconds. So we are saying in a rolling window of 1 minute, we ended up serving like 10 requests.
Exactly.
So why the problem happened? Because our window was fixed, and on the edges, this request came. So it's not. It's not always like the 5 requests within 1 minute window. Within a rolling window, we may end up getting serving the double of the request. So that's the problem with this algorithm, which the next one, the rolling window, which we are going to talk about, that will resolve that.
How are you going to serve the double of the request here? In this case, you mentioned the problem.
Yes. So let's say the 1 minute window, we have a limit of 5 requests. So and our window, let's say it's a 1 minute window. So 2 to 2.1, 2.1 to 2.2. But what happened? The window started at 2 o'clock, and like after it's a 1 minute, right? So after 30 seconds, 5 requests came. So we saw that we are in a 1 minute window and we still have the 5 requests left to be processed. We allowed that. At 2.1, other windows started, and 5 requests came until let's say till 30 seconds, we serve this 5 requests also. So I mean, with our implementation wise, it's fine. Our window was 2 to 2.1, 2.1 to 2.2. We serve 5 requests within 1 minute window. But if we look at the time, like 2:30 to 2:1:30, so this is also basically on the boundary of those 2 windows. We ended up serving double of the request. That's what this image is showing, right? So from like this 30 seconds to this 30 seconds, this is also a 1 minute window. I mean, if you see that, like, so this is also 1 minute time frame, but there are 10 requests being served in that. And this problem is happening only because we're keeping our window fixed, like 2 to 2.1 to. So there are like other algorithm where it will be a rolling window, anytime to any time. If it's a 1 minute, we should not be serving more than allowed request. So that's the, like, I believe like Leaky, I mean, this one has the other sliding window algorithm. So that resolves that problem.
Okay, so here in this diagram, right, what is the number of requests you should supposed to serve?
5 per minute.
5
per minute.
5 per minute. Okay. I thought actually we need to serve like 10 per minute.
So that is the problem we are showing here. Like,
yeah.
So logically, we are not allowed to serve more than 5 requests per minute, but the 30 seconds from previous window consumed, 30 seconds from the next one, basically the edges of them. So we ended up serving 10 requests instead of 5 if we have this algorithm in place.
Hey, 1 second. So this algorithm is same as leaky bucket. I mean, the previous algorithm, right? Every fixed interval bucket you put, then this looks same in that way.
Logically it is same, but only difference is like
we are defining, I think, based on time.
Yeah, that's the difference.
Yeah,
logically,
that's the only difference. Logically, yes. Containerization is always there, no matter it's a bucket or no matter it's a linked list. That is always there. Container is always there, but only how you are segregating or defining your token strategy, that varies.
So there were 2 parameters, like the what is the rate we are going to process and what is the refill rate. So those are controlling that algorithm. Here is the time window which is controlling the. I mean, we can say in some sense it's same, but yeah, it's different the way. I mean, they're like limiting criteria is a little different, that the refill rate and processing rate, so that can be tuned. Here is a fixed time. It's a time bound windows.
But there also time bound. Yeah, you have to. The tokens are put in the bucket at preset rates periodically.
Right. Preset time, and then we have the processing rate also. Like how are we going to like process? So that is also again another parameter through that algorithm.
So in the token bucket case,
right? It's in the first case you have a number of tokens and how many, at what rate it has to be filled, and in this case you have the number of seconds and number of requests, same 2 parameters in both cases.
It is
good
same.
point.
It is the same only. When I was reading through, the only
yeah,
thing is the parameters are different. The way they're saying it's bit whatever you said, it's right. It's to me also same. His point is there you also have a bucket and you are initializing with 5. Say for example, same example we'll take 5 tokens we are initializing per minute, and again at this minute you will do again refill of the bucket in our token bucket algorithm. So it is ended up same only. So that is his point. But the only thing is the refilling part, we have 2 different functions involved, and refueling and one more was there. What was that? The fine tuning is really difficult to manage for the different distributed system. The bucket size and the token refill rate.
Yeah, we can read up more on this. Yeah, it does look like similar.
It looks similar only.
Yeah, so refill rate will make the difference here. So let's say we have to process 10 requests per minute, and our refill rate is 2 token per 20 second. So
Yes.
here in this case, let's say when we fill that, so by the end of the first minute, we have the 10 token in the bucket.
Yeah.
We execute those 10 requests, but now when we enter in the next, so by at 1:30, so there will be only 2 tokens.
But here I have the complete.
It will not fill more than that.
Yeah, that's the one logical difference. Yeah, that's clearly
something related. I just reading this system design interview book by Alex Zhu, and one of the pros he mentions for the fixed window algorithm is resetting the available quota at the end of a unit time window fits certain use cases.
I think we should move on. There are I think Raghav is going to cover other algorithms also.
Oh, that's okay.
Let's
really going. I am learning a lot, to be honest here. Okay.
Yeah, it's
learning. I just have one question, basic question. When we say reset this bucket or reset this window, we are talking about millions of keys in this store, right? And if the window is small, the number of updates to that store is also pretty high. Have you taken this as kind of granted thing? Because I was just wondering how you would be able to do so many resets if the window is shorter.
What is your concern here?
So we are resetting the counter, not the.
No, but see that counter is different for every key, right? No, for example, if you're rate limiting on a user ID. If you're rate limiting on a user ID, for example, user ID level.
Yeah,
for example, this user ID
is only 1 or 2 different types, right? Like let's say premium will be 50 per second, basic will be 20 per second or something like that. Or
no, but still
API level. Read API will have 50 per second and write will have 2 per second.
No, but no, listen to me. My question is if I am a user A and you are user B, I am firing requests. My limits as per the window will be different from yours, right? So because my rate of request will be different from yours probably. So I'm a basic, think of I'm a kind of abusing the API and I'm using up more, right? My current counters would be different from yours, right? So I need to store this information per user level somewhere. That means that brings an additional requirement of resetting these counters for you in a different time and for me in a different time. So is my question clear?
Yeah, your question is clear. It makes sense, but the only difference is that resetting at least for this algorithm, like whatever we have on the screen right now, fixed window, it will happen at the same time for all of us. Basically, the first request from the user, you strip the second portion away, and you check is the second minute same as the earlier one. If it is, then increment the counter and check. If it is not, then reset from 0.
That is the rules, right? That you can set based on your priority level or based on your subscription.
What I'm saying is that window has to be stored separately for each level of rate limiting that you're trying to do. If it is for IP address, for example,
this window is per whatever criteria we are using, whether user or IP or whatever.
rules.
Yeah.
Exactly. So my question is still valid, right? Then when you're resetting this based on the granularity of rate limiting that you're doing, right? Those many writes has to happen within that window.
Yes.
Which I believe is very expensive. Don't
I
you
mean,
guys think?
not window for that key.
Yeah. If I say, for
key
example,
could be
1
IP
minute.
address or user ID, right? Yeah.
Yeah. If I say for 1 minute, the window is 1 minute. For every 1 minute and for every user, I need to go and clean up this window.
Yes.
No, not
Is my
required.
understanding
Not,
correct?
No. I mean, you're right, but not required for every user, whoever is active.
Yeah, whoever is active, yes.
See, one point I want to add, right? If you think like when the window size is smaller, you might not going to see much difference, right? When you think like if you have a 10 minutes time, right, you will see big difference, right? You need to think in that angle because most of the algorithms use a fixed or sliding. It might be same if you use 1 second window, right? How much difference it will make, right? You need to adjust accordingly. If you are expecting 10,000 users requests, right? You put a window of 100 means all 9,900 requests will fail, right? Those are the gambling you have to do. You need to adjust those things. But if you do bigger fixed thing, it will accordingly, it will go. Definitely everybody has
I
to
don't
bid
know.
on this one. Yeah.
Practically, yeah, I know that this is all theory, but in practically, I mean, if you have any experience, if anybody has experience, like for example, how Twitter works, right? Because they do have granularity up to, I think, minute level probably, right? So I don't know how they're managing even at minute level.
They use the
Because
product, see, there is a, if you want to learn more on this, Google has a product called APG Gateway, APIG. That's what they call APG. You can able to take, nobody is going to share how they are implemented. Okay. But as far as the APG Google product, it use a Cassandra is the database. And then you can use the multi-data center distribution. You have so many logic rules can apply for single URL. That's where it does.
So Twitter, just to add, Twitter has, I'll ping you the link also, I just looked up. So Twitter has a 15-minute window and they allow like the 900 tweets lookup, 1500 user tweet timeline, mention timeline is 450, I'll just ping on the chat. So most of the companies, they like, if you look up their docs, right? So they publish that. So I just pinged the link. So it has
they might be use some sophisticated, proxy level and so many things. They use it, make sure that, you get a better response for, for interview purpose, right? Any one of the stuff, if we can justify that, definitely it makes sense, You need to identify the number, ideal number. Like if somebody asks you to design for, handle for 10,000 requests, right? You need to come up with the right number and then, sliding window, it makes sense, any sliding window. Yeah, definitely.
Yeah,
this is a good way of going. The only thing, how APG gateway Google implements, right? When you have a distributed environment, that's the where the difficult part when you go for interviews.
I think most of the API gateway has rate limiting as a function. So even like the NGNX and all, this software load balancer and API gateway. So that also has inbuilt rate limiting. I believe like most of them has, they provide the rate limiting functionality. So I think we can go and read up more on that.
Yeah, exactly. Yeah. I think we should move on, I think, now.
Okay, I think we are coming to the last algorithm close to the one. So I have just two diagrams to discuss here. We reach to the sliding window part. So in sliding window, we have two options. So one is the log one, and the other one is just a counter one. So so the previous problem what we had is on the edges we are getting more burst of traffic. So to avoid that, what we are doing is we are going with this option here. Okay. So this example, what we're doing is we are storing and logging the timestamp into our memory. Okay. And the old timestamp, we are removing it. So if you previously discussed, a fixed window has a major issue, it allows more requests. So this algorithm will keep track of the request timestamps. So when the first request is coming, store that timestamp. Okay, so usually this timestamp, they're saying we can store in Redis, and someone else said that it can we store it in distributed. Yes, we can do that. Okay, so then the second request at the 30th second, we are storing it again. So when the next request is coming, that's coming at 50th second. So in this example, if you clearly see that we are allowing 2 requests per minute. I think something is wrong in this diagram. Give me a minute. Yeah, so yeah, this is right. So 2 requests only we are allowing. So the counter is going more than 2. That's why we are rejecting here. So when we are going to the 40th second, so that time what we are doing, the old timestamps which we had in the memory, we are deleting this.
So basically, like something like the every like millisecond or something, like anything prior to that, I mean, the older than 1 minute, you drop it.
Would be disregarding that, yeah.
Yeah, yeah. So, yeah, makes
so this
sense.
way, my overlap would not be there.
Yeah.
So this is actually sliding window, right?
Yes.
Yeah, because you put the implementation details, so it's difficult to understand.
So somebody asked a question that are we considering the drop request also in the calculation? I think we don't, right? The drop request will not be counted against the calculation. So Raghav, is that correct? So there was a question on the chat, like somebody asked, Subham, I think.
I did not look at. Okay.
So he asked, like, are we considering the drop request also in the calculation? I think it's a very good question. So let's say we have like 101 and 130, 2 requests came, and there was 1 request came, like which dropped. It came at what time? Like 150 or 14? Yeah, 1050. So the drop, so and 150 that got dropped, and now the 140 some request came. So basically,
no, I don't think we are making that into account. The reason being is because otherwise again we are confusing with the previous window again.
Got it.
The whole funda is we are clearing the old timestamps here and allowing only that number of counters if it's within the limit.
Got it.
Or the way I understood. But yeah. So this is the log one. So now the last one is this one, the rolling window with a counter algorithm. So in this is there is a formula which has been shared in the Alex book. Okay, so this is a formula which helps us to calculate how many exact number of requests if there is any overlapping is happening. So the green portion, this is the rolling minute. Okay, and this is the fixed minute. Okay, if you see the 5 request has been served in this particular portion and the 3 requests in this one. So the sliding window is more like a hybrid approach which combines, I would say, the fixed window and the sliding window together. So assume that there is a rate limiter in this example, like maximum 7 requests per minute. Okay, so the 5 requests are coming in the previous minute and 3 is coming in this minute. So this formula would applies, and based on this formula we can decide whether we have to allow 6 or 7. So if you see here, so 3, what they're saying that use this formula. So maybe what I can do is I can move this one. So what we are going to do, we are going to identify at what level of rolling minute, at what time we are getting the next request. Okay, so that would be more like your overlap percentage. Okay, so that is a factor. So here, if you see the 3 requests, okay, plus 5 requests, multiply by it at 70 percentage was in the rolling minute. You have already completed a 70% of that minute, so that would be your overlap factor. So based on that, you will come up with a number 6.5, and depend upon the use case, either you go with the lower one or the upper one, 6 or 7 you will allow. So this is about the counter algorithm of a sliding window. So I would again open this to podium here. So what do you think? Do you have any thoughts here, or you can share your knowledge with others?
Yeah, I think the purpose, for me at least, it looks like at the edge of the window, right? This kind of smoothens out the traffic, right? Instead of if you don't wait the previous minute, and so it resets to 0, right? So there is the traffic could double at the edge of the window, right? I think this kind of smoothens the traffic by waiting the previous window and the current window.
Yeah, one more thing I would like to add is the one before this, the sliding window, the pure sliding window, that's very difficult to code. It's going to take a lot of memory. So one of the things which one can do is, like, we can use an exponential moving average kind of thing. With that, you reduce the number of data you have to store. It won't be as accurate as a pure sliding window, but it's a good approximation.
Yeah, I think that's a good part. This one actually sounds like exponential average, right? You are taking the previous, you are some percentage of the previous.
Yeah, kind of.
Yeah, kind of. Yeah, and you're right. The previous algorithm, I don't think anyone implemented really in production, because you need to store every request, right? You need to store every request in memory, to at least timestamp of every request in memory.
Yeah, not just store, but also clean the.
Right, store and then clean up. Yeah. That's most of theoretical, and it provides maybe the best kind of like rate limiting, but it's prohibitive to implement.
So in this diagram, like the green part you highlighted, right? How many requests we're serving per minute? Is it 5 or more than 5?
5. I mean, 5 plus that 7.
5.
That 6.5 request. They have mentioned that formula, right? 3 plus 5 into 0.7%.
Yeah, no, one thing to remember with this last approach, it's not an accurate approach. So it's never going to be exactly 5. It could be little more than 5, little less than 5. So remember that always.
No, it should not be greater than 5, right? Because per minute we are trying to serve only 5 requests. So if it is more than 5, then it's not correct, right?
Oh, I think more than 7.
No, how it is correct? Because per minute we need to serve only 5, right?
No, it's a 7. It is 7. I think it is 7. I think what they are talking here is it is 7.
Okay, so we are trying to limit the the number of requests to 5, but we are serving 7. So that is again where I mean the server is gonna overload, right? We do that.
No, but they are saying rate limiter allows a maximum of 7 requests, right?
No, they said 5 requests, right?
Is it?
Yeah.
Okay. 5 requests per minute.
Yeah. So I think if you don't do like this, right, in a normal algorithm, it could allow double the at the boundary of the window. If just let's say second before the window start, you can have, like, let's say your size 5, right? So 5, and the second on the next window 5, total 10, right? So, but if you take a time around that, a 1 minute window, it's basically passing 10 requests within 1 minute, correct? So it could actually double.
Right.
And I think this one, by having 70-30, it will. I mean, I don't think you can avoid going more than 5, but they're limiting how much you can go up. It will not be double of that. At the worst case, you're going to do like 7 instead of 5.
But 7 also more. But the thing is, I don't think it will go to 7. I think we can stop at 5 only, because we know what is the start interval, right? And then we know what is the end interval. how much we can serve. So once the 5 requests are served, then we will not serve again greater than that until the time window.
No, it's
when
rolling.
the new window starts. Until
It's
the new
rolling.
window
It's
starts.
not fixed. It's not fixed. So
Right.
it will be like you're moving
Yeah,
it
I
slowly.
agree. I agree that point. It's not fixed. It will roll. But what I'm saying is first now the window started, right? So now we know stop window. So until the stop window means the start window will start for another, right? So until the stop window, we serve only 5 requests.
Right. So the way look at it is that I think in ideal case, right? In the whole time, in the time, like if it takes time from 0 to n seconds or minutes, right? If you take any 1 minute, right? In ideal algorithm, if you take any 1 minute starting from anywhere to anywhere, right? You need to have less than 5, right? That's ideal case, right? You should be able to take, but here we are fixing some time as a start of the window or moving it, right? So when you do that, what happens at the time, the window edge, right? If you take window edge and if you take window edge in the middle of the minute, let's say time, and you take, let's say, half minute before, half minute after, right? If you define that window as 1 minute window, now that window will have, in case of the previous algorithm, we'll have to double the size. It'll be 10 requests, not 5 requests, right? But if you use this, it will be maximum 7.
So let me explain in
How did you
another
come
way
with
why
7
your number
actually?
of requests
So
actually
how did you come
increases.
up with the number of requests is 7? You said max is 5, right? So what is the 7 where that
The
is?
7 is if overlapping is happening. What I understood is.
So here is another way. Think about this like this. So let's say that 70% window which you're seeing, the very first one, you see there is only one blue box, right? And then the second column has two blue boxes, and the third column again has 2 blue boxes, right?
Right.
And the third one has 3. Now think about this. You're doing the average, okay? When you're doing the average, that 70% had total 5 boxes. Now think of another case where we moved the whole green box a little bit to the right. Now what happened was, you see those 2 boxes and 2 boxes, the second and the third column. Now that has dramatically increased the total number. Now your new 70% plus the new 30% is probably more than your total number of requests per second, because the distribution is not uniform in that 70%.
So if I will little bit slide it here.
Exactly, to the right.
So it to the right. So it means it would be having 3 and 4.
Don't think
7.
about 2 and 3, but just think that the distribution is such that in the 70%, the initial few are very low, but the later ones have a lot of requests. So when you move the window to the right, for example, at this instant, let's say you had only 6.5 requests per second. The moment you shift to the right, even without even a single request
But
coming
my
in,
percentage is also going down, right? So the 70 will go to the 50.
Yeah, but the number of requests in the later part is much high. Even 65% of 100 is greater than 70% of, let's say, lesser number. So the point I'm saying is that even at this instance, if you have total 6.5 requests per second, when you move the window slightly to the right, even without a single request coming in, probably the number is going to shoot up.
I mean, assuming you have new request, right? After you move the
you'll get a new request. Yeah, you need a new request, otherwise it won't go up. But the number of requests per second will shoot up with just one request coming in or few requests coming in.
Yeah.
So that's the cost you pay for keeping the implementation simple.
So there was when I was reading this particular thing, there was a point it mentioned clearly. So they made an assumption that the request in the previous window is evenly distributed. They made an assumption.
Oh, okay.
Okay.
So someone asking why you have more than 5 requests, right? So think about this way: you have 2 windows, right? Previous minute, one current minute. You can guarantee 5 or less than 5 only within that previous minute, current minute windows, right? That's the only guarantee you can provide.
1 second. So we don't have previous and current window. We have window started when the request came, right? So that's where the window starts. The previous and now there's actually timing.
No. I don't think so. You maintain here. You maintain in this case a window start. You let's say your algorithm starts some point and you have a window boundary. You let's say start from 0th minute, 1 minute, 2 minutes, 3 minutes, like that. And then whenever you get request, you find out the request timestamp, and based on that you put that in the correct window. If the request is coming within like less than 1 minute, then it is in the first window, right? It'll go, otherwise it'll go to second. If the timestamps are 2 minutes, it'll be going to second window. So here you can guarantee 5 requests only within that minute, previous minute and current minute, right? But if you take, let's say first is 1 minute, second minute, but if you take a window, right, around the edge, like that edge of the first window, the rolling, if you take rolling minute around that time, if you don't do average, it's actually how much? It's actually 8, correct? So 8.
Oh, sorry. Yeah, in this example,
right?
yeah.
8. If you take that minute, right, it's 8. It's more than it's more than 5. In the worst, if you don't do this average like this, worst case can be 10, right? So because the previous window can be 5, the current
it
window
would be
5.
worse than 10. Yes.
10. So by doing this average like this, it kind of reduces. It cannot go more than. It will not be double. It will be less than.
More than
I think that's
7.
No, why are we taking average? I didn't understand that part. Why? Because the requirement is per minute we need to serve only 5 requests. So where is that we are HMB?
So
per minute that will overruled. My understanding is when overlapping happen, then we are not restricting to per 5 requests per minute.
Right. So in ideal case, right, you when you say 5 minutes per 5 requests per minute, it means, as I said, you should be able to take any window of 1 minute. It should be less than 5, right? That you cannot guarantee. You can only guarantee like a fixed. Let's say your window starts from 0, we're moving by 1, 2, like that. It guarantees from first a window of first minute, then it guarantees window of next minute. But if take any time window between those two, right, you cannot guarantee that. It can be double, right?
So now whatever algorithm we are explaining, this looks like more as like the algorithm 1, the first algorithm, the token bucket. This looks same as that.
No, in token bucket we don't do like we don't assign weightage to previous and current window, right?
If you see that, there also the problem is same.
You mean the like at the edge of window, like the,
the
count can, yeah, correct.
I mean it is right. Same, but except that 70% is 0% in that.
Right, exactly. Actually, all these algorithms suffer from that limitation. There is no way to. I mean, the only way to really get around this is the previous algorithm, where you had to store every timestamp of every request, right? If you store timestamp of every request, then you can guarantee within given any time, any window, you can guarantee, right? Because we can't store timestamp of every request, any algorithm like this, where you are moving a window of fixed size, there is always going to be, at the edges, right? You are going to exceed more than the limit. And the purpose of this rolling, the having average, is that limit can you're trying to reduce less than double. You're trying to reduce below double. It will not be more than. It will not be double.
So
I agree at any
time
point
check. I think we're almost at the end. So can we summarize? If we want, we can extend it to another session. Raghav, you want to moderate and summarize?
I don't have anything else to cover, to be honest. Last week only I started learning about these concepts and algos, and we have great people here around, so they have shared their views over here. So every algorithm, one after another, has solving another problem, but we cannot, what I understood in the summary session, we cannot guarantee the perfection here. Okay. So we are coming up with the new algorithm approach compared to the previous one, and how we are trying to solve the cons part of the previous algorithm. So we ended up with this algorithm in the end with a sliding window approach, where the overlapping issue which we were facing, the burst of traffic or allowing more than number of requests, we are trying to throttle it to the maximum bare minimum level. So ideal scenario in this algorithm, it should allow only 5 requests per minute, but whenever there are overlapping happen, instead of allowing 10, we are limiting it to 7. This is what my understanding, and how we are limiting based on the calculation, how much overlap we are having. If overlap is 70%, just previous request plus previous request in current window plus request in the current window into how much overlap we had. So based on that, we will allow either 6 or 7 requests, but not exactly 10. We will not overuse our servers by allowing 10 requests.
This is what the summary of this session from my side. I think I personally had a great learning by giving this session, because though I am a presenter, but everyone has contributed to the best level. I guess almost 10 persons actively participated. Thank you so much, guys, for helping and sharing your thoughts on this. If you have any other summary thoughts, please feel free to jump in and let's summarize this session. And yeah, all these sources and information I read it from this Alex Yu book. So this is a source of information.
Yeah, if anybody needs the book, ping me. I can send the PDF. I have it.
Yep.
Okay.
So do you have advanced version of Alex Yu?
Recording.
No, I have the old one.
So I'll stop the recording. Thank you so much, Raghav, for running this session.